We are on.
Okay, hi, I'm Margot Lockwood. This is my second summer doing QuarkNet. I'm going to quickly go over what I did last summer and then start talking about what I'm doing now. So last summer, I started calibrating this chip that's related to the high-cal Unedited project. And the chip gives the orientation compared to Anita. And so my goal was to calibrate it so we can have orientation from Anita to high-cal and measure the drift of the sensors. So this is the chip. It has 9 degrees of freedom, meaning it has an accelerometer, gyroscope, and a magnetometer. The accelerometer measures acceleration and gravity, and the gyroscope measures rotational motion, and the magnetometer magnetic fields. And it's 9 degrees of freedom because for each scope there's the X, Y, and Z direction, and you can use these to get yaw, pitch, and roll. So this is the setup. I just followed this little schematic, so it's pretty easy. And then, so I tried to play this video last year when I presented, but didn't work, so I'm hoping. So this is a little visualization of the data once I started calibrating it. It's easier to understand what's happening rather than just looking at a giant stream of numbers. That's why we decided to make the visualization, but overall, it wasn't really that helpful to have. It's kind of fun. So to calibrate it, I found the minimums and maximums of the accelerometer and the magnetometer, and then scaled these to what the correct values should be. For the magnetometer, it might not be quite right because of all the magnetic fields in the room, like the computers and cell phones, but it seems the culprit kind of accurate. For the accelerometer, here is my numbers after, so you can see laying flat, 2 of the axes will be 0, and then 9.8 for gravity, and this is consistent for all the different sides. For the gyroscope, I had to calibrate it slightly differently. I used a turntable. I figured out about what speed the turntable was going at, and then I compared that to what the chip thought the turntable was going at, and then I multiplied in the code the difference just by a scale. So, like 7.8, I would multiply 1.1, and I would get the actual 8.6 outputted. That is consistent to real life. So that worked pretty well. Is there any questions about the chip calibration before I move into the Belle?
Was your video purely of accelerometer, or was that gyroscope, or was it a combination of both?
That was a combination of all of them using some kind of yaw pitch roll thing.
Cool.
You said you had to calibrate the magnetic field for local magnetic fields.
Mm-hmm.
If you were to send it to the South Pole, how would you know the magnetic field there?
Well, I tried to calibrate it to true north, but so I don't know if that will be consistent. Maybe the same. But anything else? Okay, so. So this summer I've been working on the Belle project, and I'm getting data from a collider, an asymmetric energy collider. It's located in Japan. Lots of different scientists work on it. My connection is through Dave. And the actual collider, the goal, why the collider is made, is to study CP violation and beam meson decays, and just a better understanding of the CP violation. So I'm going to quickly explain what that is and then talk about what I'm actually doing. So this is a photo. There's Belle 1 and Belle 2. I'm looking at data from Belle 1, and Belle 2 is pretty similar to Belle 1, except it has higher luminosity, which just means more physics because luminosity is the amount of events in a certain time over the cross-section, which is the probability an event will occur. But the luminosity of Belle 1 is already impressively high, so Belle 2 is like very high. It's 40 times higher. So, and then this is some of the slides I just took from the Belle PowerPoint, but see, this is our connection. I'm pretty sure that Dave has in Moscow, so you can see all the different people in the universities working on it. This is another one of their slides, just talking about all the cool physics that happens at bee factories, what in the CP violation in the CKM matrix. So the CPT symmetry, this relates to the CP violation. The C stands for charge conjugation, so that would basically switch the charge, so switch the proton into an antiproton or just any particle into its antiparticle, keeping the same mass and opposite charge. So the C symmetry, if it holds true, then basically the laws of physics would be the same for an antiparticle and a particle. And for P, parity is for P, and it is inverting the spatial coordinates. That's pretty explanatory. So if you basically it's same as the C symmetry, for the P symmetry, if you switch the physical coordinates, then the physical laws would still evolve and act the same, and it would be a mirror image of reality. For T, if you switch the time, like complete opposite, inverting, then everything would still act the same. And you don't actually see this because the second law of thermodynamics, but that doesn't mean it doesn't hold true because of that. It's just not observable in the universe as a whole. But asymmetries for the T are observed, and it's the T asymmetries are equivalent to the CP violation, which I'm going to talk about. But so this is a little image, so you can kind of think about the mirror reality for the CPT symmetry theorem. But it was pretty interesting because it seems logical that this would hold true, the symmetry, but the CP violation was like theorized, and there's experimental evidence of that, and that's what bee factories like B was originally created to show. So in the CP violation also helped, they theorized a third generation of quarks before there was any experimental evidence of that. So it kind of relates to also what the CMS kids are doing, trying to find the fourth generation of quarks. And it also can help explain why there's more matter than antimatter. And I just thought this was kind of funny because it says CPV is a key for existence of the universe, and that's this nice little photo. But this is from the Belle side as well. Okay, so CP violations. This is just a quick history explanation. So, 1957, they demonstrated how the weak interaction violates the CP symmetry by the beta decay of cobalt-60. The mirror image of this reaction does not happen with the same likelihood of the reaction itself. And if the particles were intrinsically the same, then it would make sense that it would decay each way with the same probability. In 1961, these two other people also showed that antimatter and matter are intrinsically different with looking at kaons. Kaons can change into their antiparticles by switching some quarks, but again, like the other one, it's not the same likelihood that it will go one way as the other way. So not with the same probability that an antiparticle would turn into the particle as the particle into the antiparticle. So these two people are related to Belle, so that's also cool. They worked there and that data. So these two people, they predicted the third family of quarks for any experimental evidence. And the Belle data and the Belle, which is another big factory, supported this. And there were some Nobel Prizes for this as well. But the explanation has to do with the CKM matrix. Those are just people's last names, that's how it's named, which has to do with quark mixing, and the PMNS matrix, which has to do with neutrino mixing. And these are cool concepts because I'm like, look at it and try to actually understand how the matrix works. But okay, so the asymmetric B factor, this is what Belle is. It's called asymmetric because there's two different energies of the beams, which was before, prior to the asymmetric B factors, this was not like a common practice. So the reason why there's two different energies of beam is to help you can find the exact time things happen because you know the location from the detectors. So you have a very orderly understanding of where the decays are happening and when. But you need a lot of beam mesons to observe the CP asymmetry. It's 10 million. So they collide electrons and positrons in order to get all these. Okay, so what am I doing? So I worked to get my Belle account, which took a while of like emailing back and forth, and I was also out of town, so it took a while, but I got my data and that was very exciting and my access. So now I had to work to understand the Belle framework, working with C++, Root. I did some tutorials, and also becoming more comfortable with Linux commands. I installed a virtual box on my computer so I could run Linux, which was, it's working well so far. And now I'm looking at the electron-positron annihilations for potentially a dark photon or any just interesting physics. And this will help lead to information about dark matter if I and Dave find anything. So you look at, in order to do this, you look at the invariant mass plotting histograms, and if it's not smooth, like any narrow spikes, that can potentially lead to some interesting physics. So at the moment, I'm trying to look at just positron-positron and electron-electron collisions to have some background noise to compare to the electron-positron annihilation. So to show if there's actually anything special in those histograms. Okay, so electron-positron annihilation, this is what I'm looking at. There's a probability that so a lot of different things will happen, but right now we're interested in when it emits an electron and a positron pair or two electron and positron pairs. So that's specifically, this is the last slide as well. So special thanks to Dave, and I'm running Steven's code. So Steven helps too. Questions?
So what comes next for you?
Well, now that I'm becoming more familiar with writing code, I need to see if the positron, electron code that I added into the DX macro that I'm running actually works. So I'm going to run that job. And then I'm going to keep working, and there's various things I think Dave's going to have me do once I actually become comfortable with this. I think the dark photon was just kind of a starting thing to become comfortable with the Belle format.
This has nothing to do with your talk, but you and Finn have something happening at the Art Center. Do you want to take the opportunity to advertise that here?
I have more show cards if I can pass them around again. But so we have a show this final Friday at the Women's Art Center, and it's kind of relating to science and photography. So it's experimental. So it's really cool. Everybody should come check it out. Even if you can't come on the opening, which you really should try to make that date because we'll have food. But I just like Yeah, I know most people have already probably taken one, so you don't have to take one again. But yeah, we have some microscope photography. It's good. Oh, but so even if you can't come on the opening, it'll be up until August 8th. This is, the details are on this. But just try to stop by and check it out. Bring your family.
I said and for food, so yeah.